We have seen different types of transmission line resonators. Let us now consider waveguide resonators. At higher microwave frequencies, the transmission line resonators have relatively low value of Q. Since open-ended waveguide can radiate significantly, waveguide resonators are usually short-circuited at both ends, forming a cavity. Electric and magnetic energy is stored within the cavity. So, a rectangular cavity and a cylindrical cavity is shown in the figure. So, you can see that this rectangular cavity is essentially a rectangular waveguide, and with both the ends it is now short circuited. Similarly, it is a circular waveguide with end caps at both the ends. Now, the dissipation of power takes place on the waveguide walls as well as in the dielectric material filling the cavity if the dielectric is lossy. Coupling to cavity resonator may be done using small aperture or a probe or a loop. So, this is a aperture coupling, where through this aperture the coupling with the cavities is achieved. This is a probe coupling, where this central probe goes inside the cavity, and this is a loop coupling, where this central conductor of the coax forms a loop. So, we start our discussion by determining the resonant frequencies of rectangular cavity. So, here we show a rectangular cavity which has sides A, B and D. So, what we do? We first find the resonant frequencies for such cavity, assuming that the cavity walls are lossless and also the dielectric material, if any, present within this cavity, it is also lossless. The unloaded Q of the cavity is then determined considering small amount of loss on the waveguide walls as well as in the dielectric material. So, initially we find the resonant frequency considering lossless condition. So, for TEMN or TMMN mode, we can write the transverse electric fields in the form of E bar xy, which takes into account transverse variation, variation with respect to x and y, and this bracketed term gives the longitudinal variation, and since the cavity is closed at both ends, we also consider the reflected wave, and therefore, A plus and A minus, these are the amplitudes of the forward and backward wave, and beta mn, this is given by k square minus m pi by a whole square plus n pi by b whole square and everything under root. So, what happens now? We have at z is equal to 0 and z is equal to d, we have perfectly conducting walls, and therefore, the tangential component E t, tangential field has to be 0, at z is equal to 0, and this condition will give a plus equal to minus a minus. Et is also 0 at z is equal to d here, and this condition, once we substitute a minus to be equal to minus of a plus and divide throughout by 2j here in this term, if we substitute a minus to be equal to minus of a plus, then we can take a plus outside and divide numerator and denominator by 2j. In that case, we get Et xyd to be equal to minus E xy a plus 2j sin beta m and d, and that must be equal to 0 here, and sin beta m and d equal to 0, this implies that beta m and d is equal to L pi, where L is equal to 1, 2, 3, and therefore, for a rectangular cavity, now we can write the wave number k m n l, which is equal to m pi by a whole square n pi by b whole square plus L pi by d whole square, and therefore, for a rectangular cavity, we can write the wave number k m n l as under root m pi by a whole square plus n pi by b whole square plus L pi by d whole square. Now, whenever we have this b less than a and a less than d, the dominant mode will be TE101, and this dimension d will be lambda g by 2 for the TE10 mode. Now, let us calculate the unloaded Q of TE10L mode. For TE10L mode, we can write the field components Ey component we can write a plus sin pi x by a e to the power minus j beta z minus e to the power j beta z. So, this is the wave that is travelling in the plus z, and this is in the minus z direction, and similarly we can write h x is equal to a plus by z t sin pi x by a and to the power minus j beta z plus e to the power j beta z. And we can write h z in this particular form. Now, how we can put these forms, because we have seen TE10 mode, for TE10 mode we had Hz is equal to A10 cos pi x by a e to the power minus j beta z, and Ey minus j omega mu a divided by pi A10 sin pi x by a e to the power minus j beta z, and Hx is equal to j beta a by pi A10 sin pi x by a e to the power minus j beta z. These expressions we have already seen in our discussion on dominant TE10 mode of a rectangular waveguide. Now, what we do? We are writing A plus for this term minus j omega mu A by pi, if you compare Ey from here and Ey from here, and therefore, A10 becomes j A plus pi by omega mu A, and this can be written as j A plus pi by k eta A. Since we have omega mu is equal to k eta, and now you can see that here in this expression Hz is A10 and A10 in terms of A plus, it is j pi A plus by k eta A. So, this is how we are writing the same field equations what we studied earlier in slightly different form. Similarly, we can see that Hx can be put in the form of minus A plus divided by Zt sin pi x by A e to the power minus j beta z plus e to the power j beta z, and this Zt is actually omega mu by beta. So, these expressions we have already seen earlier, and using these expressions we can write the Ey, Hx and Hz field components in the form shown here. It may be noted that in these expressions we are only considering the waves which are travelling in the plus z direction. In cavity we consider the waves which travel in plus z as well as minus z direction. So, we have Ey, Hx and Hz components defined. So, if we substitute E naught is equal to 2 A plus by j, that means A plus is equal to E naught j by 2, then we can write Ey to be equal to E naught sin pi x by A, and this can be written as sin L pi z by d, because we have seen that beta becomes equal to L pi by d. Similarly, we can write Hx to be equal to minus j E naught by Zt sin pi x by A cos L pi z by d, and Hz is j pi E naught divided by k eta A cos pi x by A sin L pi z by d. So, once we have these field components written in this form, what we can do? We can find out the electric energy that is stored within the cavity inside this electric field Ey, and that can be computed as epsilon by 4 and its volume integral Ey conjugate dV, and when these expressions for the Ey field component is substituted and we evaluate this integral over the volume of the cavity, that means 0 to A, 0 to B and 0 to D respectively being the variation of x, y and z, we get this expression. And we know that at resonance stored electrical energy WE is same as stored magnetic energy Wm. Now, we consider the case when the dielectric is perfect, but the cavity walls are slightly lossy. So, what we can do? We can find out the power loss on the conducting walls, and that can be found out as Pc is equal to Rs by 2 integrated over the walls. We have 6 walls, and at each wall we find out mod of Ht square ds, and Rs the sheet resistance for the conductors, it is given by omega mu naught by 2 sigma. It is the surface resistivity of the metallic walls, and we can find the conductor loss So, when we substitute these field components, tangential field components, when we substitute tangential magnetic field components in this expression and find out the power loss in the individual walls and then add them together, this is the expression for the conductor loss. And we can now define QC, which is equal to 2 times WE, this is the energy stored, multiplied by omega naught and divided by Pc, the power dissipated in the conductors. In the second case, we consider the dielectric to be slightly lossy, but the cavity walls are perfectly conducting. And in that case, we can write epsilon to be equal to epsilon dash minus j epsilon double dash, and this we can write as epsilon naught epsilon r 1 minus j 10 delta, where 10 delta is the loss tangent and power dissipated within the dielectric volume can be found out as Pd equal to half volume integral of j dot E conjugate dV, and this becomes omega epsilon double prime divided by 2 volume integral of mod of E square dV, and from there if we substitute the expression for electric field, we get ABD omega epsilon double prime E naught magnitude square by 8. So, QD with lossy dielectric, but perfectly conducting wall can then be found out So, 2 epsilon prime ABD by 16 mod of E naught square, this gives the total stored energy multiplied by omega, and we have found out P d. So, we substitute the expression for P d, and then we get a very simple relation for Q d, which is equal to epsilon prime by epsilon double prime, and this becomes equal to 1 by 10 delta. So, we have seen for the two cases when the dielectric is lossless, but the waveguide walls are lossy, and in the second case when the waveguide walls are perfectly conducting, but the dielectric is slightly lossy. So, we can find the overall unloaded Q naught, as we have seen in the earlier case. 1 by Q naught will become 1 by Q c plus 1 by Q d, and therefore, Q naught will be 1 by Q c plus 1 by Q d whole raised to the power minus 1. Let us now discuss about the circular waveguide cavity resonator. Since the dominant mode of circular waveguide is TE11, the dominant mode of circular waveguide cavity is TE111. For TM modes, the mode with the lowest cutoff frequency is TM01 in a circular waveguide. Now, we can write the tangential component of the electric field in the same manner in terms of the transverse coordinates rho and phi, and also a wave travelling along plus z and minus z, and we use this to find out the resonant frequencies for the TE NML and TM NML modes of the circular waveguide. For TE NM mode, we have beta NM is equal to k square minus p prime NM by A whole square. We remember that this term, it is the roots of the derivative of Bessel function, and for TM NM mode we have beta NM is equal to under root k square minus p NM by A whole square. From the condition that E tangential is equal to 0 at z is equal to 0, we get A plus is equal to minus A minus. Now, when this condition is substituted for the expression of the tangential electric field, we will get a term which is sin beta z, and we know that Et will have to 0 at z is equal to d, and that means sin beta n m d should be equal to 0, and from there we get beta n m should be equal to L pi, and therefore, the resonant T E NML modes we have the resonant frequency given by F n m L is equal to C by 2 pi root mu r epsilon r P prime n m by A whole square plus L pi by D whole square, and that for the T m n m L mode we have F n m L is equal to C by 2 pi under root epsilon mu r P n m by A whole square plus L pi by D whole square. The Q factor for the cylindrical cavities we can find out adopting the same procedure and considering first lossless dielectric and the cavity walls are lossy, and then we can consider the Q factor for the cylindrical cavities can be found in the same manner as in the rectangular cavities, and we can first consider the case when the dielectric is lossless, but the cavity walls are slightly lossy, and then for the second case when the cavity wall is perfectly lossless, whereas the dielectric is slightly lossy, and then find out the unloaded Q as in the case of rectangular cavity. Cylindrical cavity operating at TE011 mode is often used in the frequency meters because of its higher values of Q. This type of frequency meters are used in as direct reading type microwave frequency meters. So, we have seen different types of resonators, the transmission line and waveguide type resonators, and we have seen how near resonant frequency we can find an equivalent RLC representation of a transmission line type resonator. In the next module, we will discuss about power dividers, directional couplers and filters.